All right, everybody. Sorry about the delay. So, welcome back. Today we're going to continue where we left off. If you remember from last time, we started talking about the life cycle of a process. And among other things, we said that you start up with a new process. That's the new state. Things are not yet ready to run. There's a bunch of work that's done, at which point it's put onto the ready queue. And everything that's on the ready queue is potentially runnable. And so at that point, the scheduler makes a decision, pulls one off, runs it for a while. There's an interrupt that happens, probably a timer interrupt. We're back to the ready queue and so on. We go for a little while. And then eventually we try to do I.O., which takes us off the run queue, puts us on a wait queue associated with what we're waiting for. And by the way, the scheduler at that point would have grabbed somebody else to run off the ready queue. And then when our I.O. comes in, we're back on the ready queue. We're ready to run. We go for a little while. And eventually we exit. And at that point, we go into a zombie state. For what reason? Yes? That's right, so that the exit code can get back to the parent. And if the parent's gone, to the grandparent, and so on. Does anybody know kind of what process tends to be the parent, the super parent of everything? Yeah. Yes, init. Init is the super parent. And so eventually init will clear it out. The other thing is, we looked at code like this for threads. So we've been talking about threads as a useful programming technique, and we're going to really move into synchronization by the end of the hour today. But here we see, gee, there might be a good reason to have some threads going on here because one of them is busy computing pi to the last digit, and if we didn't have another thread, then this other thing would never run at all. Okay? And, you know, what does it do? Well, thread fork here is kind of an abstract idea, but basically starts an independent thread running the given procedure with the given arguments. In this case, we each have one argument. And the behavior is now you actually see the class list. Okay. And if you only have one hardware thread, then the threads are going to be alternated to give you that idea that there's more than one thing running simultaneously. Were there any questions on this? Okay. So now at the very end, we kind of looked at code like this. Okay, and I think I wanted to very briefly come back to it because I'm sure you have mulled over it for a couple of days. But if you look at all that this code does is if it starts at A calls B goes into an infinite loop which just does yield over and over again, and assume for a moment that we have two threads S and T that are running that code. And by the way, let's assume that S and T have been running for a while. We'll try to figure out how they get started up in a little bit, but let's assume they've been running. And then if that's true, here's an example of what the stack might look like. And remember we talked about stacks last time as well. But here, thread S kind of has a stack which shows you A's stack frame and then B's stack frame with this while. And then at some point, yield is a procedure. And yield is actually a system call. So it calls into the kernel. Okay, and we switch over to the kernel stack. Why do we switch to a kernel stack instead of the user stack? Go ahead. Yeah, you have no idea whether the user has a good stack or not. So we put it on the kernel stack. That's what this light red is. And then it calls switch. And then what happens? Well, switch, if you remember, all it does is it saves out all the registers in the context state of thread S. It loads all the registers in the context state of thread T, and then it returns. And as a result, switch returns to run new thread, which returns to yield, which returns to B, which then goes back to yield, and so on. But notice, it's a different stack frame. Okay? Now, how many people think this is kind of weird? Okay. How many people are completely okay with this? This just makes perfect sense, okay? A couple of you. Would you like me to talk a little bit more about it? How many people would like me to say a few more words about it? Okay, so how do you think about this? So the way you think about this is that imagine for a moment that there is no T. Okay, so what would happen? Thread S is the only thread in the world. It has A stack frame, which calls B. B calls yield. Yield calls run new thread. Run new thread picks a new thread. Run new thread calls switch. There is no new thread, so the best that run new thread could do is pick S again, right? So when we get to switch, really nothing interesting happens. It switches, S's registers for S. And now what happens? Well, after switch is done, it does a return, which takes the switch frame off of the stack. And then that returns from run new thread, which goes back to the user, which then returns from yield, which then goes back to the while loop, which then calls yield again, which then calls run new thread, and then we get down to switch and go back and forth. Okay, is everybody with me on that? So if there's no switching, this is just call down, return, call, return, call, return. Okay? How many people are okay with that? Okay. Anybody have any questions on just that basic idea? Because really, what's interesting is look what happens with switch. When we return from switch, we go back to run new thread. So run new thread picked a thread. We call switch, switch returns. It just happens that when switch is actually switching to something else, what does it do? It changes the stack state to T. And so, T had happily been running earlier, went all the way down to switch, and then got switched out. And when we come back to it, we reload T's state, and it's like T never left, and we just return from switch, and then we return from run new thread, and we get back up to the while loop again. And then we just keep ping-ponging back and forth. And switch here, all that switch has done is switch has switched out all the registers for S and the stack pointer for S and any other state for S, and it's switched in T's state, and then you just return from switch, and voila, you're in that whole different stack frame. Okay. Questions? Yeah.
Why do we need to run two threads with the same code? Like, is this just an example, or typically in the real world, would you have thread S switch to something else to kind of maintain parallel?
Well, the only reason, this is clearly an example I picked to help explain what's going on. If you had something completely different, you'd switch to that. There are lots of examples where you want to run the same thread. You're not going to run this because this is boring and pointless, right? But you might run two things that are both computing different parts of a graph. If you're, you've got a Go game that you're trying to solve or whatever. Yeah, go ahead. No. Good. I'm glad you asked that question. No. The switch on thread S switches out all the registers for S, switches in the ones for T, and then it just returns. So it's not calling. What it's doing is it's swapped in the stack frame, and so now it's like it's a different instance of switch because there's a different stack frame. So when I return to T's run new thread on T's stack. Not call, it's returning, which is a little weird. Yeah, question?
So run new thread selects the next thread that gets run, whether that be T, U,
Yep, or S.
Which actually loads the registers.
Yes.
So run new thread has to store the selected thread in kernel memory, correct?
Well, in fact, when I do a system call, I'm saving a bunch of registers so the kernel doesn't mess up the user. And so really, run new thread can call switch with an argument that says, this is what I want you to switch to. Or run new thread could push it on the kernel stack or whatever. Whatever mechanism for communicating between run new thread and switch, that's what you do. Good. All right. Any other questions? Yeah.
Switch is the kernel stack. Does it mean every time you call switch, create a
No, that's that. Now remember, see the bottom thing here? Assume S and T have been here for a long time. So those stacks already exist. So the only thing when T first ran and called yield, it put this on the stack. And then we abandoned T. We left T's stack and everything alone, and we started running something else like S. And so that's just sitting there waiting to go. And so when S comes down to the switch, all we do is we switch in T's state, and then we return as if we never left. Okay? Good. Yeah, question. Kind of weird, right? Yeah. I will show you in a moment how it looks when we're just starting, because I know you're all sitting there. This is all fine and dandy, but how does it start? I'll get you there. Question, yeah. It doesn't return to the other thread. We switched in the other thread so that when you do return, it pulls the return code off of the stack. It just happens to be a different stack, and so when I return, I'm returning up this side of the stack. Remember when we looked at the call stack, right? Every time you call, there's a return information that's in there, right? And what we've done by switching to the other thread is we've switched over all of the information about what stack it's using and so on. And so when we return, we're really returning up this level of stack, which is at a different address than the other stack, because we changed the stack pointer. Okay. Have we overdone this example, or is there any other last questions, or should I let it go? All right. Good. I'll avoid, singing about let it go, let it go, let it go. Okay, so you guys probably don't know about that movie because you don't have young kids. But okay, so what happens when the thread blocks on I/O? So let's talk about that for a second. So we're busy running our code, and we execute a read system call. And what happens? Well, when a thread requests a block of data from the file system, there's a good chance, maybe, that read actually has to go all the way to the disk, which means what? It means we want to put the thread to sleep, right? Because we want somebody else to run. Why waste time while the thread is waiting for its disk operation? And so what happens is the read, of course, is a system call. Notice that's read and not fread. Everybody see that? System call, we get to the kernel half of read, which really means after we save all our registers and change the kernel state and so on, which starts the read going on the disk, and then it calls run new thread because we're blocking on I/O, which calls switch, which switches to another thread, like T, for instance. Okay, and again, the same idea happens here. And, this is similar to all sorts of different things. So the communication between threads is like wait for signal join, like networking. All of these things are similar to this model that I just showed you here. So anytime we call into the kernel with some system call, could be a join, could be a network call, could be a read, we do the operation, we decide that we're going to have to block, and at that point we call run new thread, which calls switch, which then, poof, there's a new stack there, and we return, and some other thread is running. Okay? Poof. Questions? Now, you might ask yourself, all right, what if a thread never does any I/O, never waits, and never yields? Okay, well, then you got a problem. Okay? If Compute Pi grabs all the resources and never releases the processor then and doesn't print to the console, then basically that run new thread or that Compute Pi thread just keeps going forever. And you have to find a way to regain control. So what was the way that we talked about regaining control? Yes? Huh? Timer. Great. An interrupt. Okay? So how do we do that? Well, we utilize external events like interrupts, timer, etc. The interrupts could be from actual devices like the network I/O or like the disk coming back or whatever. Or, it's important to always have a regular source of interrupts so there's always an interrupt every so often so that we always switch. Okay? And And if we make sure that these external events happen frequently enough, then we make sure the dispatcher runs, and we constantly run new thread and switch, and so then everybody gets to go. Okay? So how does that look? Well, let me talk a little bit about interrupts again. So we talked about interrupts from the hardware standpoint kind of a few lectures ago, but here we are running some code. There's some assembly language code, and an interrupt comes in, and typically that interrupt comes from the interrupt controller, which you might all remember. And there was an interrupt. And what happens is the interrupt causes the processor to stop what it's doing, and typically if you've got one of these really deep 20 or 30 stage pipelines, the first thing that happens is the pipeline flushes out, which is kind of unfortunate, but necessary. And then the processor dispatches to a handler to handle that interrupt. And of course, we've got to save all of our PCs. As I mentioned, we disable every interrupt for a moment, and we go into kernel mode, and then the first thing that the handler does is it turns off the interrupt that came in. So if this is a network interrupt, the first thing is it sets the mask to disable network interrupts, and then it re-enables all interrupts. So I had several questions after that first time I talked about interrupts about, well, why do we disable all interrupts and re-enable all interrupts? It's exactly so that this little tiny process there where it's not a process, that little tiny set of instructions where we essentially turn off the network interrupt while we're handling it, and then we can re-enable all the other interrupts. Okay? And then, of course, we save the rest of the registers, and we dispatch to the handler, and then that's when we grab stuff out of the network. And now we're going backwards. We restore the registers, we clear the current interrupt by talking to the interrupt controller and talking to the network. We redisable all the interrupts, and then we do fix the priority back to where it was, and we do a return from interrupt, and we pick up where we left off. Okay, so this is a good pattern for what happens in a typical interrupt. Okay, and this funny thing about raising priority, lowering priority, that's really saying certain interrupts are more important than others, and if we're dealing with a network interrupt, we make sure to definitely disable the network interrupt because we don't want that to keep happening, plus maybe other things that are at the same level as the network. And then we go through, we do stuff until we actually update the network hardware by clearing its interrupt, and then we go the other direction, undo things, and continue. Okay, so that handler there that's in green, that's an example of code that might invoke the scheduler or whatever to schedule another thread if it was the timer interrupt. Okay. Now, I want you to notice something here. So notice that we're running on the user mode. We hit the interrupt, and now we enter the kernel, and now we're going to get a kernel stack. That's part of the dispatch to handler. And that kernel stack is now going to run stuff to get moving, and then we restore and go back the other direction. But when we restore, in that case, this is after switching, and we'll restore to a point at which the other thread was running, if you think about how the timer interrupt works. So what's weird about this is if we're using this as a timer interrupt, we have the original S code up there, we go through the interrupt, and then when we come back, we're running the T code. It's going to be what's going to happen. Okay, now ponder that for a second. If you look here, this is kind of what that means from a stack standpoint. So we're busy doing something. The timer interrupt comes in. We hit run new thread and switch, and then we return our way up the stack. And when we return from the timer interrupt, rather than returning back to some routine, we return back to T, or a different thread. Okay? And what goes on during the timer interrupt, typically there's housekeeping of some sort about whatever's going on, and we just call run new thread. Okay, questions? Yes?
We return all the way back up to T, so if this was like a thread S, and we switch to a thread T, return back to above subroutine?
Well, so this sum routine might, suppose it's S. And S is running, and then the interrupt comes in. Remember how in the previous 2 slides ago we had a yield that took us into the kernel? Here the timer takes us into the kernel. But after that it's all the same because we call run new thread, we call switch, takes us over, and then we could go back up the stack for T. Okay, and the only difference between what happens here and what happened here is that rather than us getting to run new thread by calling yield voluntarily at the user level, an interrupt is taking us in here, which call new thread switch. And then when we come back over here and work our way back up, we could go to T just as if we yielded, except that we've triggered this with an interrupt instead. Okay? Good. Questions? Were there any questions on this? I kind of popped through here pretty quickly. Nope. Good. All righty. So I'm about to tell you how we create new threads here in a second. So let's make sure that the timer interrupt makes sense. That infamous question that was asked earlier, but what if S and T aren't already running? Does this still work? Yes. I'll show you in a sec. Okay. Ready? Should we move on? Okay, so thread fork creates a new thread. So what is it? It's a user-level procedure that creates new thread and places it on the ready queue. All right? So remember that diagram of states? There was new, and that led to ready. So thread fork is somehow going to take us from new to ready. And arguments to thread fork are, among other things, a pointer to the actual routine we want to run. So what's the code? A pointer to an array of arguments, and then a size of the stack to allocate. Now, different thread forks are all a little different in how they work, but by and large, somebody has to tell the kernel or whoever's creating the thread how much of a stack. Remember that little discussion we had about making sure there's enough room? Okay. So how does this work? Well, just like with any system call, we sanity check the arguments, we enter kernel mode and sanity check again, allocate a stack and TCB, and then initialize the TCB and place it on the ready list. Well, what's a TCB? Thread control block. Okay, now I had a couple of perfectly good questions of, well, you said process control block, but now how is that different from a thread control block? And so as you can imagine, if we have multi-threaded processes, a process control block has a bunch of thread control blocks inside of it, and the thread control blocks are the things that we put on wait queues. Okay? That's not rocket science, but thought I'd mention it anyway. So how do we initialize the TCB and stack? So we have to sort of set registers fields of the TCB to reflect the fact that this thread is not yet running. So wait a minute, what did I mean by that? If you look, what is the state of a thread after switch? The state of a thread after switch is it's hanging out in memory with a stack that looks like switch had just taken away from it, or taken the processor away from it, and it's just waiting there. And if we ever switch back and then return from switch and so on, the thing is running, right? So it'd be nice if we could somehow, when we make a new thread, make something that looks sort of like this, so that when switch returns to it, it starts the thread. Okay, so what did I mean by that? So here we go. I didn't say about this yet. So basically what we have to do is we have to initialize the thread control block with the right thing. So there's a stack pointer made to point at the user's stack, the return address, which is a special routine called thread root, and a couple of argument registers, including the code that's actually going to run, and the array of arguments are going to be in, say, A0 and A1. And we don't bother initializing the actual stack itself with values, because what we do is we start thread root at this thread root stub, and then we got to think about this as if the stack frame was just before the body of thread root. Okay? Just before it gets started. So if you look, this is our initial stack. It's like we have a fake stack frame with nothing on it right before everything starts. And when we switch to it, then everything happens. So if you look, here, we're busy running, say, S, and there's no T yet. So S what I didn't tell you was, well, S actually came from thread root, which calls main, which calls up, which called A, which calls B, which calls yield, which calls run new thread, which calls switch. And this thread root stub is actually sitting on the sitting in a TCB ready to run on the ready queue, and switch just saves out all the registers for the thread on the left, loads the registers for the thread on the right, which, by the way, there isn't very many. There's the A0 and A1, which are the code that are going to run, and the array of arguments. And the PC is at this thread root stub, which is a little bit of code that gets us going. And as soon as we start running, things will pick up. So what does thread root look like? Well, thread root starts some housekeeping, which is basically, when did the thread start up and so on, so we can compute how many cycles are used. It goes into user mode from kernel mode. It calls the function with the arguments, and then it calls thread finish. So if this code were to run from start to end, we would, start some housekeeping, turn into user mode, run the function, finish, exit, we're done. Okay, but we know that we're going to be switching back and forth, so somewhere when we're in the middle of calling the function pointer, it's going to yield or interrupt and go over a different thread. So startup housekeeping includes things like recording start time of thread and other statistics. And so here we go. What happens as soon as we switch to that stub is it calls thread root, which calls thread code and starts going, and the stack just starts growing and shrinking. Okay, and the final return kind of cleans up the thread. And so if you look, that's basically all that's involved. So you could think, what is that thread code? Well, that might be A from the previous slides, and it'll call B, which will call yield, which will call switch, which will go back over to thread S and back and forth. Okay, and so this thread root stub, which calls thread root, it's almost like it unpacks itself into a running image of a thread, and from that point on, we end up looking like we did on the slide where S and T were going back and forth. Okay, questions? Yes? So in this case, thread root is it's like the parent stack frame of everything. Yeah. It's not really on the bottom. It's the thing that's running, and it's eventually, for instance, when this thread code returns back to thread root finishes from here and calls thread finish, at which point we have to go back into the kernel to exit and throw it out. Good. Okay? Question? Yeah. So the overhead with creating threads is, we got to create all the structures in the kernel, TCB. We've got to enter, thread fork's going to enter the kernel to set all this stuff up. We'll talk about non-kernel threads in a little bit later in the lecture. There's some overhead in allocating some space for the stacks and getting all that ready. So there's some, the housekeeping work takes a little time. The nice thing about threads in general is you're not going to the full extent of creating a brand new address space because it's just a thread and not a process, and so it's a lot cheaper typically than a process. Okay? And we can even talk about how to make threads even cheaper to allocate. We will a little bit later. Question? Yes? Say that again? Well, when you call thread finish, depending on your thread package, it's going to put the TCB in a zombie state in case it's joining with somebody. Okay? Or if you're doing thread finish, it may be that there's a different thread that's busy waiting for it, and it'll wake that thread up before it exits. So thread finish is kind of what happens when a thread exits code, which is just similar to what happens when a process exits. If you could imagine, we were talking about zombie states. This might put the exit code, if there is one, in the TCB and take the TCB off the run queue and put it in a space where it waits to be joined with the parent thread. So this is the code that basically deallocates the thread. Okay. Question, yeah? Well, thread create ultimately invokes the code that calls for thread root. Thread create is really setting up that whole environment. So what is thread? Thread create basically creates a new stack frame, sets up the stub, sets up the registers that are in the new TCB to point to things like the function we want to call, and then that's it. And it's only when we switch to it to start running that then thread root gets called and so on. And so thread root is the execution consequence of calling thread create, but thread create does a lot more. It has to set up the environment, get things ready to go. Thread root is a routine that will be running in the thread, whereas thread create is kind of like a routine running in the original parent thread. That's another way you could think of that too. Okay? Good. All right. I see a couple of shaking heads. Are there questions? Yes. When will the interrupt happen for a timer interrupt? Yeah, so the timer interrupt is not going to impact threads that aren't running quite yet, because until the thread is packaged up with a new TCB and it's put on the ready queue, the run new thread isn't even going to know about it. So if you look back at this interrupt routine here, so we were busy running something, computing pi. We get an interrupt. It goes to run new thread. Run new thread wouldn't even know about the new thread until it's ready to go and on the ready queue. And then switch isn't going to know about anything that it hasn't heard about. So switch is not going to go to this thread root until it really is ready to run. And then at that point, switching to the thread root, which unpacks the code and starts it running, isn't any different from switching to something that has been there for a long time. Good. Okay. So I'm going to move on. So waitlist closed last Friday. Early drop passed. I've heard from the TAs that there are folks that are asking about what more resources can they look at, what other things can they read. Believe it or not, the textbook is actually pretty good. Okay, it's one of the better OS textbooks I've run into. The dinosaur book is not too bad. That one I think you could probably get at one of the libraries. There's also a book which I will put up on the resources page to read, but I would start by reading your textbook if you've got some questions, because that really is very good. Okay? And the other thing is I try to have some readings up on the schedule, but those readings, I haven't checked them recently. They get moved around by various people teaching the class, so I'm happy to bring that back. Or if people see something that's inappropriate, let me know, and we'll fix it, because who knows what they did to the readings that I put up there 5 years ago when I first did this. So 4 years ago. Group sign-ups. All right, so don't miss this. Deadline's tomorrow. Hopefully you got your groups together. What you should do is definitely go to your section. If you don't have a group, let the TA know. Okay, because what's going to happen is we're going to try to give you a chance to find good groups, and then we need to put everybody in a group. So people that don't have groups might end up in an arbitrary group, which could be fun. But if you don't have a group, definitely let your TA know tomorrow. Okay, because tomorrow is the day. And then Tuesday is when you sort of say what your TA preference is, and then we run our TA assignment algorithm, basically, to figure that out. So tomorrow will be the last free choice, the last time that you can go to whatever section you want. I don't know, take advantage of it. 4 people in a group. And then next week, next Friday, you'll have an actual official section. okay? And remember, starting next Friday with your new TA, you want to make sure you know your TA. You want to make sure your TA knows you, okay? That's going to be a very useful thing, and I highly recommend it, okay? And they'll be taking attendance and figure out who's in what sections and everything. So, and I think that's all I had to say on Administrivia. This is kind of a stall week between, getting the final set of class and getting a final set of people in the class and coming up with the actual groups and so on. So I don't have a lot of exciting Administrivia. Any questions? Okay, so what is this thread abstraction? Let's look at this a little more. Because as we move into using threads and synchronizing, which is where we're going next, we have to start asking, what are we assuming? And the assumption is that the programmer assumes a thread is like a CPU that's just running, okay? And every thread has its own processor. The reality is, of course, there's a finite number of physical hardware threads, and so the scheduler has to make choices as to which one runs at which time. So what's interesting about that is while the programmer abstraction of everything's always running all the time might be useful, the physical reality is that things are not always going to run all the time. So for instance, if you had a thread that wrote something, was going to write something in a variable, and another thread that was spinning, waiting for that variable to change, that might or might not work the way you expected it to, because the thing that's spinning might run for a long time, and the thing that's going to write isn't even running. Okay, so there's a lot of weirdness that's you got to start thinking about when you think about threads. Okay, they're not always running all the time. The other thing is you could go the opposite direction and say, well, I happen to know that threads are not running all the time. Maybe I know I only have one hardware thread. Therefore, I can go ahead with this thread and modify this data structure. Even though I know two different threads may do that, it's okay because, only one thread runs at a time. Okay, that's also faulty thinking because there is this interleaving. And so it could be very easy that you're starting to modify in one thread, it gets interrupted, the other thread starts modifying, and now your data structure is a mess, which is exactly why we're going to have to deal with locking and synchronization. Okay, so keep in mind that this abstraction of, many things running at once is both not true and true at the same time, and you've got to be careful. So the programmer's view, for instance, is, well, this thing runs, and it, increments x, y, and, adds 5y to z. But a possible execution is that, or, it runs x equal x plus 1, and then it goes off for a long time doing something else and comes back. Or, it does the first two instructions, goes off for a long time, comes back. All of these different interleavings are possible, and so one of the things you need to do in the case of multi-threaded code is you got to make sure you design it in a way that works no matter what the scheduler decides to do. Okay, and it's easy to not think properly about this, and we're going to try to get you to think defensively about how you program your multi-threaded code in a way that's likely to work. It's going to be very important. Okay? So, for instance, thread 1, if we have 3 threads, it could be thread 1 runs all the way to completion, and then 2, and then 3. Okay? Or thread 1, 2, and 3 are running at the same time. Or thread 1, 2, and 3 are interleaved in some weird way. So these are all possible interleavings. The only reason I'm hammering this point home is you got to make sure when you know that 2 threads or 3 threads are working on the same piece of data, you got to make sure that you've designed your code in a way that handles all possible interleavings, because the scheduler will do the thing. There's a Murphy's Law of scheduling. It will do the thing that screws you up the most, okay? It's like there's a little malicious scheduler whose job it is to find the bugs in your synchronization. Okay, and the only way around that is to think properly about this, and we'll try to get you some ideas on how to think about that. So, I just thought I'd throw this up there. I showed you the process life cycle. There's a similar kind of idea with threads. You create a thread. It's on some ready queue, ready and running, go back and forth. It may be waiting on I/O, and it exits. So what you can imagine about this is the threads we've been talking about so far are like mini processes that don't change their address space. So if you have two threads in the same process, they do switch back and forth in the kernel. Okay, and the thread control blocks are the things that are put on the ready queue, not the process control blocks. Okay. Now, in a little bit, I'm going to tell you some alternatives which are cheaper than kernel threads, but don't behave quite so cleanly. All right, we'll talk about that in a sec. So, we talked about thread control blocks. What is that? Well, it has the execution state, CPU registers, program counter, pointer to the stack. It's got scheduling info like the state and the priority and the CPU time. It's got pointers to stuff, like scheduling queues that it might be on. It's got pointers to the process it belongs to, right? Maybe you're going to need to add stuff to your process control blocks. Who knows? The OS keeps track of the TCBs in kernel memory, okay, in an array or a linked list or whatever. That's what we mean when we mean it's an OS thread or a kernel thread. It's actually something that's managed by the kernel. Okay. Now, what is this is the easy idea. What's a multi-threaded process? It just looks like this. Each PCB points to one or more TCBs. Okay? All right. Questions? So switching threads within a PCB. So if I go from one TCB to the next and I happen to know it's in the same process, then the good thing about that is I only have to switch out CPU state. I don't have to change the address protection state. But if I go between two threads that are in different PCBs, now that switch routine needs to not only unload and reload the register state, but also things like the protection state. So when we talk about paging and the various registers that control page tables and so on, we'll talk about how the fact that when we switch between processes, we're actually switching out which page table is active. Okay. And I think you talked about page tables in 61C, or yeah, I thought so. So, okay, this is not a complicated slide. Are there any questions? Good. So, what are some examples of multi-threaded programs? So, embedded systems, you could imagine that you have a different thread for different parts of the program, and so embedded systems have all sorts of threads. Modern OS kernels, there's also lots of threads inside the kernel that only stay in the kernel. They do housekeeping, they do file system flushes, they do all sorts of stuff. As long as you're within the kernel, this is almost like there's one big process, which is the kernel, because the threads are not are at highest priority in the kernel. Database servers, you can have a thread per user, for instance. Network servers, oftentimes there's a thread per flow. So if you've got one video going through a router and a different video going through the router, there might be a thread associated with that. Who knows? There might be threads associated with updating the routing state. And of course, file servers, web servers, we all kind of dealt with that. If you really do have more than one hardware thread, you might use threads to get parallelism. So a good example here is you have a task that you can divide up into little pieces. You make a bunch of threads. Now all of a sudden each thread can work on a little piece. Okay? That's called multiprocessing in that instance, because there really is multiple things going on at once. Multi-threading has the concurrency and potential that becomes multiprocessing when there's more than one actual physical CPU involved. Okay? All right. So here's a typical use case, for instance. Here's a client browser and a web server. So the client browser has many web servers it looks at, because you've got a lot of tabs maybe. Maybe you've got pieces of a web page that come from different servers. And then, of course, the web server is getting incoming requests from lots of other clients. And so both client browsers and web servers are multi-threaded. Okay, so threads are just an easy way to look at this. Now, we're going to start the process of understanding why threads are a good programming abstraction that's easy to think about. But you could imagine that one useful thing for a web server, why do we want threads in the web server? is there's a request that happens to have I.O. Well, the thread will call the kernel and it'll go to sleep, which is fine because a different thread from a different client is busy accessing the web cache. And so the nice thing about having threads in a web server is anything that needs to block the thread because there's an I.O. operation doesn't get in the way of all the other stuff that's going on. Okay? And the same is kind of true of client browsers. Most modern browsers, when you go to a website that has 12 million pictures and a bunch of text and a bunch of other, and your Twitter feed on one side and all that sort of stuff, there's many threads, even within the page, that are talking to remote servers to pull it in, so you get to see sort of some of the things show up first, even though some of them are slow. So what's some numbers here, okay? So these are good things to have in the back of your brain. So when, for instance, oops, almost lost my microphone. So, for instance, the frequency of performing context switches, 10 to 100 milliseconds is not uncommon. That's how often you do it. Context switch time might take 3 to 4 microseconds. Okay, so that's much longer maybe than you thought. It's not just a few instructions. Context switch time increases sharply with the size of the working set, however. So if you switch from one thread to another, but those two threads are using completely different large amounts of memory, there might actually be more time spent in the hardware cache pulling things out of DRAM than the actual instructions for switching. Okay, so there's a lot of time in the working set, and we'll talk more about that as we go on. So the moral of this slide here is just that context switching depends mostly on cache limits and the process of the thread's hunger for memory, not so much on the actual instructions for the switching. So, because if you looked at that switch routine I showed you last time, there aren't a lot of instructions in it. But the cache can be very expensive. So here's another thing here. If you look, you go to a Windows task manager or you do PSAUX with the right flags or you PS with the right flags so that you can see the process groups. And what you might find here, for instance, is something like Thunderbird. Here it's got 28 threads. Okay, why is that? Well, they're synchronizing different, might be synchronizing different mailboxes. They might be with your different folders. They might be doing something. Who knows? They might be virus checking. So there's a lot of stuff dealing with Windows and so on. So multi-threaded processes are common. Okay, Firefox is a consumer of many threads. Okay, so what are some use cases in the kernel? So some use cases in the kernel are things like a thread for each user process. Well, that is like an abstraction where you say, well, I have the user process. There's a thread that takes over when we enter the kernel. Okay? There might be a thread for sequencing steps in processing I.O. So if I've got a device driver that's going to go push things out from the file system to the disk or pull things in from the disk, I might actually have a thread to do that. I might have threads for device drivers, etc. So the kernel has a lot of threads in it. That's a new thing. 20 years. So what it used to be in the old days was there was kind of one thread of execution in the kernel at one time. And the reason they did that is because the kernel is doing stuff that really cannot afford to get screwed up. And so by having only one thread, you didn't need to have synchronization. Once you entered a system call and you were running in the kernel, you knew for a fact that no other thread was in there messing with your data structures. That's fine, except, then we got multi-core and hyper-threading and all that sort of stuff, and it made no sense to block up the kernel like that. And somewhere around the early 2000s, Linux went from having a single big lock for the whole kernel to a whole bunch of small locks so that there are many threads running simultaneously inside. And that was a big transition called on by multi-core. So multi-threading is kind of the name of the game. All right? And so what we're going to do now is let's take a brief break. Everybody stand up and stretch. And I'm going to switch out the battery on the microphone just since it's red. I think we're back. So just to briefly show you some of the different cases here. So how do we put this all together? So a Unix process basically has what? It has a memory space, which is this yellow thing. It's got stack in the memory. So this would be like a single threaded process. It's got I/O states, such as open file descriptors, etc., sockets that are in the process. It's got CPU state, like PC, stack pointer registers, etc. And so the resources are things that are protected. There's a sequential stream of instructions, and the process control block / thread control block, because this is a single-threaded process, is stored in the operating system somewhere so that switch can get at it. Okay? So this is the simplest model for what I was calling a heavyweight process a while back. So if you have a bunch of heavyweight processes with one CPU, then we just switch between them the way we talked about. And this is a great example of switching from one thread in one process to a different thread in a different process to a different thread in a different process. And so that means that switch routine has to unload not just the CPU registers and so forth, but all of the memory protection state, whatever that is. We haven't talked about it yet. And so on, and load in the next. Okay? And so the overhead of switching in this instance is a bit high because we've got to change the memory state. We've got to do a bunch of stuff, the housekeeping, okay? Typically, the CPU state is a low switch. The memory I/O state's a little higher. To create a process, this is potentially an expensive operation because we've got to make the process. We've got to create a new memory address space, which is a page table structure, etc. Protection, yeah, we protect every process from the other one because every time we switch processes, we put it in different protection states so the two processes can't mess with each other's memory. Oops. And the sharing overhead, however, is pretty high because if one process wants to talk to another process, right now the best that it can do is open a socket between them or something, or use some kernel call for a remote procedure call in order to communicate. So this is kind of the heaviest weight example of what we could do. What else could we do? Well, we could have threads instead. So threads within a process. Okay, so now the switching overhead is smaller because as long as we're only switching threads, we don't even have to switch out the memory state. And only occasionally do we switch between processes. Okay? So thread creation may be cheaper because we're not creating an address space. Are things protected? Yes. The memory and I/O state between threads is not protected because that's the whole point of threads. They share. Between processes, of course, they're protected. And then the sharing overhead is low between the threads because they just use memory. Okay? They write to one thread writes to memory, the other thread reads from memory. That's great, except that now we've got all sorts of sharing problems which we're going to have to synchronize with. So we've created a different problem, which we'll get back to. Question, yeah? So this is switching CPU states low. We just save out the registers and load them back in. Question, yeah?
So how does fork work with at file descriptors and stuff like that, where they're protected, right? So only one file is active, more processes are active.
Well, fork. So what does fork do with file descriptors? Does anybody remember what fork does with file descriptors? So we had an example of the web server where we forked and immediately we had to close the file descriptor for the listen socket on the child and for the new connected socket in the parent. So what happens with fork is fork actually duplicates not just all the memory state, it also duplicates all of the file descriptor state and everything. Well, the model with a parent-child with fork is that the child is doing work on behalf of the parent, and so the fact that it's sharing all the file descriptor state actually makes sense, right? Now, oftentimes, as we just said by the web server example, the duplication you get by through fork is more than you need, and so then you close a bunch of extra file descriptors. But fork absolutely copies all the file descriptor state. That's what it does. Okay. Now, in thread fork, since we're not dealing with any of the protection, you just get the file descriptor duplicated because the two threads are just in the same address space. Okay. Good question. Yes.
So just to recap, the threads are switching within the processes by the CPU, right? So if you have process 1 and you have a thread 1 in that, that would switch the threads inside process 1 before going to another process.
So that's an interesting question. So the question was, so you got this diagram here. What I see in this diagram is it must be the case that we switch all the threads within a process before we switch processes. That was your question, right? So maybe. So the thing that you got to realize, and this is, I keep mentioning this a couple of times, the scheduling policy is an interesting variable in this. What is the scheduling policy you want? So it may be, for instance, that you want to make sure all the threads have equal CPU time. In that case, maybe it would make sense to try to swap between the different threads in a process and then swap out, so that might save memory. On the other hand, it may be the case that certain threads are more important than others and higher priority, in which case you may run all the high priority threads in each process, so you keep switching processes to do the high priority threads, and then eventually you do the low priority threads. So there may be many different policies in switching between threads. So this diagram is not intended to indicate that you're going to run all the threads in process 1 and then in process 2 and then in process 3. Okay? But that's a great question. Okay. So, any other questions? Now, let's talk a little bit about this. So what we've been talking about so far is what I would call kernel threads, or kernel-supported threads that are native in the kernel. That means the threads are created through a system call, and the threads run, the kernel knows all about the threads. When the threads block on I.O., the kernel knows about it and could put it on an I.O. queue, okay? And each thread is totally independent of every other thread. So it doesn't matter that thread 1 in process 1 goes to sleep, thread 2 can keep running. Okay? Now, this is very flexible. For instance, one process could have, remember we saw Thunderbird had 28 threads. Why does it have 28 threads? Well, half of them might actually be sleeping, waiting for I.O. to occur. They're sleeping on sockets. They're waiting on disk drives. Some of them are waiting on the user to click the mouse, whatever. So that's great. The downside is they're a bit expensive because we have to do system calls to get there. The kernel is responsible for creating them and scheduling them. And if you look back here, nobody asked what I meant by low-ish. See the thread switch time down there in the lower right corner, low-ish. The reason is that if we have two threads in process 1, and thread 1 writes to a variable and thread 2 reads from the variable, yeah, the variable part of that is, there's a single memory location, it's fast. But in order for thread 1 to communicate with thread 2, what actually has to happen is thread 1 runs, it writes, and then it has to be switched out, and then thread 2 takes over and picks up and so on. So there's actually a thread switch involved in all communications in this mode. Okay, so there's actually, the scheduler gets involved here, in case you hadn't thought that through. Okay? So a lighter weight option is actually what we call user-level threads. And so here's an idea here. The lighter weight option is the user program provides a scheduler and a thread package, and you may have several user threads per kernel thread. So here's a kernel thread, the kind we've been talking about, and on top of it is a bunch of user threads which represents little chunks of code that have a PC and register state that are running, but the scheduler of the kernel has no idea that what's up there is up there. All that happens is we're running at user mode, and the user mode code has its own idea of scheduling, and so the user code is running along, and it does its equivalent of yield, but what yield really means is don't make a system call. Call the library, and the library will swap out your registers and swap in some others, and that's really fast because I don't go into the kernel. Okay, and so this is all done as a user library. Okay, now there have been many names for this over the years. The one that tends to stick with me is this is often called green threads, which I'm not even sure what the origin that was. Maybe it's not burning a lot of power and therefore it's green. I don't know. But the idea there is the user libraries are doing all the scheduling of the threads, and the kernel has no idea that this one thread that it's getting CPU time for is really being multiplexed up above by a bunch of other threads. Okay? So this is very fast, and it's switched by a yield-like library call, very cheap. Creation is very simple. It's like malloc of a little data structure, and suddenly you got a thread. Okay? The problem, of course, is think about this for a moment. This thread is running along, and it tries to do I.O. and goes to sleep on the I.O., and suddenly all of the threads are gone. Why? Because that whole thread package of threads got put to sleep inside the kernel, and so none of the ones that were running up at user mode get to run again because the whole package is sleeping. Okay, so while this is very fast, it has a problem when you start blocking on I.O. Now, there's a lot of interesting research that was done on this. There's, in fact, something that came out of University of Washington called scheduler activations, where the kernel was told a little bit about the fact that this was happening, and so when a thread would go to sleep on an I.O., the kernel would send another thread back, and so there was always the same number of kernel threads at user mode. And so that's one way to get around this. So there are many threading models, okay? So just wanted you to be aware that you can have kind of this one-to-one user thread to kernel thread idea. This is what we've been talking about kind of all lecture. This is this many-to-one. There's a many-to-many. That's kind of more what scheduler activations look like. There are many ways to try to optimize for the cost of crossing into the kernel and back. Now, Linux has made kernel threads reasonably inexpensive, and so if you do the Linux threading, it's pretty fast, and so oftentimes people don't bother with these user mode packages. But if you want to have really fast, cheap threads, because your programming model needs lots of threads, then you go to something probably like the many-to-many model is a pretty good one. Question, yeah? So the many-to-one model does not use multiple cores. That is correct. So you probably you want to be in something like this many-to-many model. Yeah. Good. Okay. So threads are useful. User-level parallelism, high I/O latency. There are many options. Early Java, there was a user-level library, one multi-threaded process, and the library did all the switching. So that's probably the kind of Java you dealt a lot with, 61B. Sun OS and Linux variants, there are many single-threaded processes. User-level library for thread multiplexing. Windows had some options. Basically, we could go through all of these, but those variants I showed you earlier, they're all over the place. There's lots of variants, many-to-many, many-to-one, and so on, and they all have their advantages and disadvantages. But for instance, in early Java, you might have a lot of threads going, but if any one of them went to sleep, then the whole thing went to sleep. So that was a many-to-one option, which is probably not what you thought you were getting. Okay. So when we add multiple cores, now this gets more interesting, because if we have two threads, doesn't matter which process they're in different cores, then the communication can be extraordinarily fast because both threads are scheduled. One of them writes, the other one reads, and we're good to go. Okay? And maybe we have 4 of these threads are running at a time. And then, of course, when we put hyperthreading, which I'll remind you guys what that looked like. So hyperthreading, the idea here is this is regular superscalar, where each line represents a clock cycle in time. A yellow block or a colored block represents a successful use of hardware resources. So that might be an actual add or a divide that's properly going on. So the way you look at this is you say, oh, in this cycle, I had 2 things going on at once, 2 instructions. Here, because everybody's waiting on a divide, whatever, nothing was happening. Here I got 2 different things running, etc. So that's the parallelism in the pipeline. That's 152 or 252. You guys take that, you find out about it. The problem with this, that works great, and that's what all of these processors that you're using these days, even your cell phone, do that. Notice all the gray, though. That's wasted. So a different alternative that people did was you put two processors together. So that's two of exactly those things. I doubled my resources. The hyper-threading alternative says, I'm going to make up for the fact that there's a bunch of gray in here by scheduling a green thread instead, I don't want to confuse from earlier, a forest green thread and a mustard yellow thread. And as a result, there's less overall gray, okay? And that's hyper-threading, and that basically gets you multiple things going on at once, okay? And so as a result, I could have 4 cores, 2 hyper-threads each, and now I could have up to 8 things running at once, okay? So these are all the different options. Okay, I don't want to belabor this point. Questions? So most operating systems have either multiple address spaces. They could either have one or many, or number of threads per address space. Some of the early operating systems like MS-DOS and early Macs were kind of one address space and one thread per address space. A one address space with many threads per address space is kind of where the embedded systems are, the kind of things that might even run Martian rovers and things like that. Traditional Unix was kind of one thread per address space, but many processes. And then kind of we're over in down the lower right here is kind of the mode we're in now, where there's many processes, many address spaces, many threads per address space, and pretty much all of the modern OSs with modern processors all kind of run in that direction. Okay? All right. So I want to start us today in the remaining time down the path of saying, okay, if I've got 2 threads and they're sharing information, how do I make that actually work? Because that's going to be messy. Okay, and here's some definitions that you may or may not remember. So multiprocessing means there's more than one CPU, so there's multiple things actually happening at once. Multiprogramming is really when there's multiple jobs or processes going together. Multi-threading is there are multiple threads per process. And just because I have multi-threading doesn't mean there's multiple things happening simultaneously, just that there's the potential for multiple things. So that bottom one is kind of what we often call concurrency. You're sort of allowing for more things to happen at once, but really it's interleaving is the minimum. And the top one here is what happens when you start adding multiple cores or hyperthreads. And what does it mean? So all of these things up top are forms of concurrency, which whenever you think you got concurrency, it's time to start worrying that you use your data correctly, okay? You got to be careful. So for instance, what does it mean for 2 threads to run concurrently? Well, the scheduler is free to screw you up, basically, right? It can run the threads in any order, any interleaving, FIFO, random, maximum. It'll read your code, it'll call to the cloud and find the maximum interleaving that's likely to find the worst bug at the latest time in the morning when you can't handle it because you haven't had enough coffee. So basically the scheduler is not your friend, okay? And the dispatcher can choose to run each thread to completion or in time slices, whatever, okay? And so here's multiprocessing, where A, B, and C all run actually simultaneously. Here's multiprogramming, where A, B, C could be run sequentially. They could be interleaved, whatever. All of these are instances where you got to think carefully. And amusingly enough, or not, one of the things that can sometimes screw people up is they think concurrently, I've got 2 threads going, and the scheduler does this serial A, then B, then C, and their code doesn't run correctly because they were assuming there was at least some interleaving. Okay, so, all right. So correctness for systems with concurrent threads is if the dispatcher can schedule threads in any way, programs must work under all circumstances. Can you test for this? What do you think? How many people think you could test for all possible interleavings of threads? Okay, how many people think you can't possibly test for all possible interleavings of threads? Okay, yeah. So, how do you know if your program works? Okay, that's quality assurance's problem. You send it off to them, they'll make sure it works for you. Okay? No. And just look, what about independent threads? Well, if you have two threads that share no state, then you can probably be able to think about them independently and get the right answer, okay? Because they're not sharing state. And you can get deterministic output, where the input state kind of determines the result. And it can be reproducible, okay? You can recreate the starting conditions in the I.O. And the scheduling order doesn't matter if switch isn't broken, right? So that's all great. The problem is that we're mostly here. Threads are cooperating, and then shared state between multiple threads, non-deterministic, non-reproducible, non-functional. Non-deterministic and non-reproducible means that bugs can be intermittent. Okay, what's our favorite word for that? Anybody know what intermittent bugs? Think physics. Okay, Heisenbugs, right? Because Heisenbugs are the bugs you get when you see a bug, and so you now put printfs in to start finding the bug, and the bug goes away. Right? The mere act of measuring the bug causes it to go away. And then you remove the printfs, and it comes back. And so what do? You ship with the printfs, right? Okay. So it's much better to design your code correct by design. So interactions complicate debugging. Is any program truly independent? So if you are truly paranoid, you might say to yourself, well, wait a minute. They're all sharing the operating system, so there are shared structures inside. And so that's going to cause that non-determinism. You're sharing the file system. Okay, so an example might be buggy device driver causes thread A to crash, independent thread B follows, right? I think one of my favorite examples is the evil C compiler example. I don't know if they give you this in any of the security classes, but the idea is it modifies files behind your back by inserting errors into the C program, unless you insert debugging code, and then it flips a switch and gives you correct code. Okay? All right, now, there was actually some examples of compilers like this that got out. But a different thing that you should think about is debugging statements like printfs could actually overrun your thread stacks. And so suddenly you put in printfs and the thing stops behaving correctly, and that's because you're overflowing your stack. Okay? By the way, these are all time. I'm trying to scare you straight in this, right? So non-deterministic errors are really difficult to find. There's many examples. Original Unix had a bunch of non-deterministic errors. My favorite thing is IBM 36091 had an operating system that was shipped, and the very first version of the operating system had 1,000 what they called APARs, A-P-A-R-S. Anybody know what that is? They were anomalous problem reports that basically were unsolved. So they shipped the thing with 1,000 Heisenbugs, okay? And that's what they did, okay? And so something which does interesting I.O. can cause deterministic errors. So for instance, you probably all heard some of the examples where you could use that to break a password, but you also use it to make good passwords. So the way you get good randomness is they have you type at the keyboard enough, and there's enough randomness in there that injects into the system to generate good keys, right? So why do we even cooperate? Okay, so people cooperate, computers should cooperate as well. So advantages, you can share resources. One computer, many users, right? One bank balance, many ATMs. Speed up. Two different things working on the same problem is faster if you've got multiple CPUs, right? Modularity. Believe it or not, compilers, like the C compiler, actually has a series of things that are piped together. So there's a C preprocessor, there's a couple of passes through the code, there's an assembler, there's a linker and loader. They all are divided up and pipe into each other, and as a result of that modularity, it's easier to think about the little pieces, and it's faster because you've got threads. Okay, so after you're afraid of non-deterministic bugs, you should not just throw out threads. Threads are useful. And I want to, for one thing, you could imagine that a high-level example of the web server we talked about, right, where you have a server loop which accepts a connection and processes a fork and so on. And as a result of no cooperation, then the server is really slow. And by having multiple threads, we could potentially make it faster. Okay? We did a multi-threaded version, which is not using processes, and you actually do thread fork. That can be faster. It looks the same, but it's cheaper and faster. And this has a much lower per-process overhead. And, would a user-level many-to-one thread package make sense here? Well, probably not, right? Because blocking is a problem. Okay. So, denial of service attacks. We'll talk about all of this next time. What I do want to say is how many people have heard about the mess with Wells Fargo today? Okay. So we'll talk about thread pools. But our first example, which we're going to dive into next time, of why synchronization is useful is we're going to look at this idea of different people getting access to their money on a common shared server. Well, what happened with Wells Fargo is there was a machine room in Minnesota. Okay? Jack is laughing at me because I know he's from Minnesota as well. So both of us are from Minnesota. But there was a machine room in Minnesota that some smoke caused the anti-fire suppressant to happen, and the whole machine room went offline. And as a result, people couldn't get their money, their cards didn't work, and basically people who had Wells Fargo's accounts were in trouble. So that could be a counterexample to, is it a good idea to share or not? I don't know. But in conclusion, we talked about, again, the fact that processes have two parts, threads and concurrency. Give the concurrency address spaces for protection. We talked about the fact that various textbooks talk about processes, but really it's about concurrency and address spaces. Concurrent threads are useful, and we're going to talk next time about how these concurrent threads cause a lot of problems, which we're then going to fix. So sign up for your groups. Don't forget to do that by tomorrow at midnight, and then Tuesday you're going to sign up for which TA you want. Have a great weekend.